I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics, medicine, nature,
or
Space. Time.
The brain. Life.
The universe.
This week, from arsenic to adrenaline, we're delving into the sinister science of poisons.
Plus, training machines to identify a baby's cry and the science behind New Year's resolutions. I'm Izzy Clark.
I'm Georgia Mills, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
First up, why a type of sugar might be behind the spread of a superbug. Clostridium difficile is a type of bacteria commonly found causing problems in hospital wards. It leads to diarrhoea and is responsible for thousands of deaths every year. But it hasn't always been such a big problem. Since the 2000s, one strain, or ribotype in particular, has been spreading faster and becoming more dangerous. Antibiotic resistance is part of the problem, but now a new study has revealed another culprit may be in our diets. Here's study author Robert Britton, Professor of Microbiology at Baylor College Medicine.
We wanted to understand why they're doing better in the environment. So one of the things we tested was whether or not there were certain sugars or other types of carbon sources that ribotype O27 strains liked better than other C. difficile strains. And we stumbled upon this disaccharide of glucose called trehalose. And so while we were testing this, we found that the ribotype O27 strains do much better on trehalose. But what was more surprising is we found a second ribotype O78, that could also eat low concentrations of this sugar. And this ribotype is also an epidemic and hypervirulent ribotype of C. diff. So it was very striking that these two very unrelated ribotypes had both acquired this ability and both started causing major epidemics around the early 2000s.
And do we know why that timing is important, or why the early 2000s?
Well, we investigated the mechanisms for how trehalose was able to be eaten at lower concentrations in both these strains, and they were completely independent. And so what was the key driver of why these emerged in the early 2000s? And what we think has happened is that trehalose is a sugar that the food industry for a long time has wanted to use as a dietary additive, but unfortunately it was very expensive to produce, and it cost $700 a kilogram prior to the year 1995. A low-cost production method was invented in that year that drove the price down to $2 to $3 per kilogram, and that made it very attractive for the food industry to use. And it was approved for use in the United States by the FDA in 2000 and in Europe in 2001. We think that's the key link.
Okay, so we've got this evidence that these two very dangerous strains both have separately got this ability to break down this sugar. And it's also the timing of the sugar becoming available in Europe and America coincides with when these started to become dangerous. But do we know for sure it is this sugar that's causing it, or could it be something else and it's just a coincidence?
It is an association, and there's no way of going back and for sure proving this. But we think that the tipping point for these two strains was really the addition of trehalose. And the fact that we do see increased disease severity in our mouse model, which is associated with what we see in humans, is also a striking coincidence. And so we hypothesize that this is the case, and we hope that this stimulates future clinical research to see if limiting trehalose in patients that have these types of C. diff in their intestines will improve their outcome.
That was going to be my next question. Where is trehalose found?
Well, trehalose is a sugar that's found in many different products. Unfortunately, we don't know exactly which, because that level of description on our labels isn't always there. But if you look at the generally regarded as safe report by the FDA, what we find is that it's basically anywhere you would put regular table sugar, sucrose. You see it in standard things you'd imagine, like ice cream and cakes and other candies, but you also find it in ground beef, pastas, bread, sushi, things that you may not even really think that there's a lot of sugar in, but in fact it is added. And so, it's hard to know exactly how much and where it is, but it clearly has inundated the market since it was approved.
Okay, so not very easy or practical to cut it out of our diets then. So what about in hospitals? Is there anything practical we can take forward from this?
Well, I think at this stage, the research certainly suggests that we should do more research to see if limiting trehalose in hospitals will help drive down the emergence of some of the ribotype O27 and O78 hypervirulent strains, and if we can also impact the health of patients that have this by altering their diet and not providing them sugars that make this disease more severe. I'm hoping that that's where future research will go in the clinic.
That was Robert Britton, and that work was published in the journal Nature.
Time to scan the tech horizon for 2018, and some of it looks out of this world. Getting things into space, be it satellites or people, is a challenging feat, and SpaceX plan to launch their newest rocket, Falcon Heavy, later this year. Angel investor Peter Cowley is here to tell us more. So, Peter, it sounds like private companies are getting involved in the space race.
Yes, hello, Izzy. Yes, because there is actually money to be made, and it's been done for many years. In the 50s, it was definitely governments doing it, and then the military got involved. But if you mention GPS, that can only be done from space. We all use GPS in our sat-navs. Telecoms, telephone calls, TV, a lot of that's from satellite. But new things like imagery, crops, deforestation, mining, etc. To give you an idea, there are 8,000 man-made objects up there that are bigger than about 10 centimetres across, of which about 1,700 are actually in use. And of those, just using the USA figures, 60% are actually commercial. The other 40% are military and government.
SpaceX have said that this year their latest rocket, Falcon Heavy, is going off into space. So tell us about it. What is it and how does it work?
Yeah, first of all, SpaceX is one of the several companies that a guy called Elon Musk, who's quite well known, certainly in the tech industries, has built, including Tesla Motors, which you might have heard of, and Solar City. He employs about 70,000 people in total, of which 7,000 work for SpaceX, which is sort of heading towards being profitable because it puts launches satellites for people. Now, the Falcon Heavy is obviously his heaviest one, his biggest one. It's got 27 engines and it's got the thrust of the equivalent of 18 jumbo jets. All the three rockets, it has three rockets, are reusable, which actually makes it cheaper because they come back down to Earth, land, and can be reused. It'll take 64 tons into low Earth orbit, which is actually quite a lot smaller than Saturn V. Some of the listeners might remember the Saturn V that launched the moon trips in the late 60s and 70s, which actually carried 140 tons. But the aim of this, apart from taking stuff up into orbit, is to actually get to the moon with humans and then potentially to Mars. First launch was supposed to be 2013, was supposed to happen this weekend, actually. It hasn't happened. He's actually going to launch his own very first Tesla car there, and it's being sent on a trip to Mars, this thing, so it won't come back again. And he's expecting to charge about £90 million per launch, so therefore there is actually a commercial model.
My goodness. And, I mean, is there much competition out there for launching things into space?
Yeah, I mean, originally, as I said, it was governments and then it was the European Space Agency. Nowadays, I've found over 50 companies that are actually will put something into space for you. A whole new industry is called New Space, which includes things like nanosats, which are tiny 10 centimetre by 10 centimetre by 10 centimetre cubes, which schools send up. There's energy harvesting. There's even funeral services.
And what are those nanosats used for?
They're used for experimentation. So this is going back to research, but research of all kinds of things in weightless conditions or outside the atmosphere.
But take it to the extreme. What about me? Is there a chance that I could spend a holiday in space?
There is, and I'll give you some figures. I don't know if it'll be a holiday or not, but SpaceX have actually got two people who paid a deposit to go up into space later this year, whether that happens or not. But work out some pricing. The sort of pricing that seems to be on the internet is probably between $250 and $500 million for each trip around the moon. Now, if you take the average, apparently according to Mumsnet, that 10%, he pays 10% of your annual wages on holidays, that means you've got to be earning between about $1 billion and $2 billion, of which apparently there are 20 or 30 people in the world that do that.
Oh, wow.
If you go to capital, because remember it's a holiday in a lifetime, then there are actually several thousand people that could afford $100 million plus. I doubt that includes anybody here in the studio. It certainly doesn't include me.
Oh my God, I better start saving then. But why are companies investing in space when arguably we could look at other opportunities for improving infrastructure, say like here on Earth?
Yeah, that's been a question for many years, and NASA's been pushed back a lot of times over the years about the expenditure. There's just general human nature, the fact that people want to explore, want to not to conquer, but want to understand new things about life. There's also a lot of other things. We've had people in the studio talking about terraforming. This is the concept of converting another planet for normal life. So if we really do break this planet, which there's still a good possibility we will, maybe we have to move some of the population away from the Earth. Maybe we're too many people from this Earth to support. And there's a whole stack of other things like asteroid and moon mining for materials. There's scientific research itself. Some things can only be done from space, as I mentioned earlier, the schools. And then a lot of things have been generated from the space program. Integrated circuits, long time before you were born. The space program did that. Freeze-dried food, that actually came out of that, etc. Metal-coated plastics. There's a whole stack of things that come out of that. But in the end, philosophically, I couldn't say definitely we should spend it on health as opposed to space or vice versa.
Fair enough. And finally, would you want to spend a holiday in space if you could?
A, I can't afford it. B, I can't justify it. And the C, actually, there's quite a lot of interesting places to see on this Earth.
How much of a carbon footprint is involved in all of these missions going up? Is it sort of equivalent to planes going around? Is it the same kind of ballpark?
It will be. If you take the thrust of 27 jumbos, then you're going to be generating that much carbon from that. Exactly. If you do that per person, if you take 17 jumbos, which may be 500 people, that's 8,500 people travelling for a period of time. You've got 2 people going up there. Clearly, there's no comparison there. Clearly, it's a lot more. There has to be other reasons for doing that. It'd be a long time before we can use a non-carbon-based fuel to get up there. There is the talk of electric aircraft, and that may well happen if that electricity had been generated, say, by another source other than carbon, nuclear or whatever, or wind, then that would not generate the carbon in the motion. But you've still got the manufacture. Cradle-to-grave carbon production needs to include actual manufacture and disposal as well.
Brilliant. And finally, you mentioned that there was a launch planned recently and it didn't happen. How much of these companies is a bit of grandstanding? Like, how much of it do you think we'll actually see?
I'm confident it'll happen. I'm confident they're far enough through with this. Remember, I'm involved in startups, have been for a very long time, and people promise things and they fail, and they promise things and fail. But in the end, they do get them. Most of them will get there if they've got enough money to do so. SpaceX has been around quite a long time. It has launched. Last year it's supposed to have launched 14 or 15 satellites into space in 2017. So therefore it can do it and it can achieve it. But this is a big, big rocket, and there's an awful lot of design work necessary. So I'm confident it will happen. Whether it's already a few years late, whether it'll be another few years, who knows?
Peter Cowley, thanks very much. Got a biological brainbuster or a chemical query? Ask the Naked Scientists.
I just wanted to know about sleep paralysis. Is it a disorder or condition, and can it be cured?
How much energy is in moonlight, and could solar panel technology be used to capture this energy?
When you cook food with any alcohol, how much, if any, percentage of the alcohol stays behind?
Every Friday, the Naked Scientist and Cape Talk unravel the science behind those weird and wonderful questions you've always wanted to ask. Download and listen for free at thenakedscientist.com/ask, or simply search and subscribe to Ask the Naked Scientist on your favourite podcast app. Still to come on The Naked Scientist, does mixing drinks make you more drunk? And talking of toxicity, we size up the science of poisons. Before that, how do you teach a machine to listen? Georgia has this report.
If you listen very, very carefully, can you tell the difference between the following 2 sounds? Here's sound 1. And the other one. Okay, that was pretty easy. But if you were teaching a computer to tell those sounds apart, how would you go about telling it what makes something very clearly a dog barking and what makes something else a baby crying? This is something one company in Cambridge have been working on.
Audio Analytic does a completely new type of sound signal processing. We call it artificial audio intelligence, and it looks at giving computers the ability to respond to sounds, such as baby crying or glass break, as opposed to speech or music type signals.
Dr. Chris Mitchell is the CEO and founder of Audio Analytic.
One of the shortest descriptions I've seen of what we do is we're like the Shazam for real-world sounds, which I think is a reasonably short way of describing what we do. It's technically highly inaccurate, but it's very short. So, yeah.
And so how are you teaching a machine to tell apart sounds?
So first of all, you need to get the sounds. One of the fundamental problems we have is what's referred to as a zero data problem, which means that there is no data to train a machine off. And However clever AI is, it's not clever at all if you don't have data trained off in the first place. So we had to go out and collect the data. That means literally smashing, crashing, bashing, and beeping our way through all of the sounds you can possibly imagine. Once we collect all the data, you then got to go through and label it. Then you move on to the more AI side of it, which is then trying to model these sounds and the combination and ordering in which they occur. Now, that is very different in itself from speech in the fact that there's no language associated with sounds. So you and I having this conversation is governed by a relatively formal communication structure. We both understand, we know the rules of it, around it, and that means that at a sound analysis level, you can sort of guess which sounds are going to come where based on those rules. My dog doesn't really have a sense of those rules in any meaningful sense, so that doesn't apply. So a lot of that language, technology, and other aspects that you would approach from speech side just simply don't translate, and hence you have to build a whole new set of AI to be able to accurately detect and respond to those sounds as they occur.
So the process, vastly simplified, involves breaking the sounds down into tiny components and getting artificial intelligence to learn which components come from which sounds and in what context. But I was most interested in the side of data collection, especially the sounds of smashing windows. Now, a lot of this happened in a soundproofed porter cabin in Cambridge, where I was shown their glass-breaking rig.
Yeah, so my name's Maury Grieve, so I'm the Data and QA Manager at Audio Analytic.
So I can see a sledgehammer in the back there. It looks very exciting. So I'm going to smash this window.
So you're going to smash it, correct. So what we'll do is we'll get you kitted up, safety equipment. You'll be behind the glass break rig, so you'll be as if you were a burglar breaking into the room. It may take you several attempts. It's actually a lot harder than a lot of people think. I mean, a lot of people think you can just, tap the sledgehammer to the glass and it will break. But in reality, you do have to give it, a reasonable kind of amount of force in order to break it.
I'm so excited. I cannot tell you how excited I am to swing a sledgehammer into a window. This must be the best place to work ever.
No, it's great fun. Yeah, it is. It's all a bit of an initiation for everyone when they start.
Right, so I better get kitted up then.
Yeah.
Where's us? I can see.
Yeah. So, what size? These.
Now, I was wearing about 5 layers of protective clothing to prevent glass from shredding me, and ear defenders as it was incredibly loud. So, as fun as this was, not something to try again at home. And believe it or not, it took 7 attempts with a sledgehammer to get through a pane of the famously breakable material glass. But eventually. And so what's the point of this learning to hear for machines?
There's security and safety applications to what we do. So if we're selling into cameras that people install in their homes, detecting whether the windows are smashed and then sending you a text message alert is obviously extremely valuable in terms of being able to do that, through to sort of modern smart speakers and understanding that the sound environment in which you project sounds, if you can have an understanding of that, so if you know that you're frying bacon, that has an impact if you're trying to play jazz while you're listening to that sort of understand that broader scene from a sound point of view is very important as well.
Oh, I see. So I have this problem when I'm trying to listen to my podcast while making dinner. So how would understanding the sounds help me, I suppose, listening to my podcast?
Well, speakers are generally at the moment are pretty dumb. If it could understand that I don't know what you were making, but let's say we go back to bacon. I sound like I'm obsessed with bacon, but fair enough. If we go back to the bacon piece, knowing the sorts of sounds involved in that, and then inflecting the way the music is produced so that it sort of has the best chance of getting over the top of that sound and around it, means that you'll be able to enjoy your podcast while still cooking the bacon in this case.
And how accurate is this, I guess, compared to humans? Because quite often we mentioned babies crying. I've been spooked by what I thought was a baby, and it turned out to be a fox in the garden screaming. So are there any sounds it's confused by, and how accurate is it?
It's highly accurate in the metrics we use. There are inevitably things that will sound very similar to it and will confuse humans if you want to use that as a metric, which some people do. So, for example, I have an engineer who's extremely good at reproducing a baby crying. Very, very eerie. Now, it's taken him many years to be able to reproduce that, so I don't know how much of a practical that problem that is. We've also seen in, say, we got a large deployment in Europe We saw there was a specific type of a bird that's kept in houses, especially in the south part of France, which sounds exactly like a North American smoke alarm. They are literally identical, and the guys had to spend a bunch of effort getting rid of that to make sure that they could be discerned. So you do come across these instances, but generally it's highly accurate.
You could hear there Chris Mitchell, CEO of Cambridgeshire-based company Audio Analytic.
And now it's time for our regular Mythconception. As we're just coming out of the festive period, Katie Hale is here to debunk a few untruths about how we can reduce the effects of getting a bit too merry.
First up, let's start before your big night out. Lining your stomach with a good meal will stop you getting drunk, right? Wrong. Having food in your stomach will only delay the rate at which your body absorbs the alcohol you're drinking into your bloodstream. So you might not feel as drunk as quickly, but drink enough and you are going to get drunk, whether you had dinner or not. But because it slows down how fast you're absorbing alcohol, eating a meal before you go out could be worthwhile in order to avoid getting too sloshed too quickly. Fast forward through the evening and you're on your night out and making your way back to the bar for a second drink. But what do you choose? It's commonly believed that mixing different types of alcoholic drinks can make you more drunk. Nope. It's how much alcohol you're drinking, rather than where it's come from, that's important here. Be it from wine, beer, spirits, or whatever your tipple. Of course, different drinks contain different amounts of alcohol and are served in different quantities. Whereas a 330ml bottle of a 5% lager packs about 1.7 units, a 250ml glass of a 12% red wine contains 3. Handily, you can get a grip on how many units are in your drink by a simple equation. Strength, say that red wine which is 12% alcohol, times volume, say 250ml, divided by 1,000 equals 3 units in your drink. The strength will be displayed on the bottle. So next time someone tells you not to mix your drinks, you can both thoroughly dispel them of that notion and reduce your chance of getting invited to the pub again. While mixing drinks doesn't make you more drunk, this doesn't mean that alternating between tequila and Sauvignon Blanc is a good idea, as it can affect you in other ways, like upsetting your stomach or making it harder to keep tabs on how much alcohol you've imbibed. Interestingly, a 2003 study in the journal Alcohol and Alcoholism suggests that the bubbles in fizz may increase the rate at which alcohol is absorbed, leading to, as they put it, more rapid or severe intoxication. But it's worth noting that there were only 12 participants involved. Oh dear, your night's taken a turn for the worse and you've overdone it. And you've got a busy morning the next day. Why not have a coffee? That'll sober you up, right? Sorry. Once the caffeine from your latte kicks in, you'll feel more awake. But it's not actually making the body metabolise the alcohol any faster. As a rough indicator, 1 unit of alcohol is processed by your body in about an hour, but this varies for lots of reasons, including your age, sex, weight, and metabolism. So why not stop the search for a sober solution and just keep tabs on how much you're drinking?
Thanks, Katie. And if you've come across any suspicious sounding science, get in touch by emailing chris@thenakedscientist.com and we can take a look.
I'll definitely be trying to keep dry this January, but will I make it through the month? Or will it, like many New Year's resolutions, end up a shattered dream, discarded after mere days? Most people do approach New Year's resolutions with the idea that it will kickstart a permanent change in our behaviour. It goes from a slog to an automatic habit. This is what's known as reaching a habit peak. But why do we make a New Year's resolution in the first place, and do they really work? Izzy spoke to psychologist Benjamin Gardner from King's College London.
There's a popular myth out there that it takes 21 days to form a new habit. And I've looked into the source of this myth, and it comes from a book that was written by a plastic surgeon in America in the 1960s, in which he found that among his patients, it took them an average of 3 weeks to get used to their new appearance. Now, as far as I know, that's the sole evidence base for this claim that it takes 21 days to form a habit. Around 10 years ago now, a colleague of mine at University College London conducted a study in which to study the habit formation process in humans. And what she found was 66 days was the average amount of time it took for people to reach their habit peak. Some people reached their peak in 18 days. Other people didn't reach their peak at all in the 12 weeks. But it was forecast that if they kept going, after 254 days, they would reach their habit peak. So there's great variation between people, between different behaviours. years in regards to the length of time it takes for things to start to feel like they're becoming an ingrained part of our everyday routine.
Now, I have to ask, is there anything special about the 1st of January in terms of changing this behaviour? Why do we even have this New Year's resolution?
Well, I think it's helpful in one aspect, in that it gives us something specific. We know that we are going to start our behaviour change attempt on the 1st of January. And it's a general principle of behaviour change that the more specific your plans are with regards to not only what you're going to do, but in what situation you're going to do it, the more specific our plans are in that respect, the more likely we are to stick to it. But I think, on the other hand, I don't think there's anything particularly special about the 1st of January. So it's useful to have a concrete date in mind with regards to when you're going to start changing your behaviour. But it doesn't need to be the 1st of January. You could equally set your behaviour change start date as, say, the 1st of February or the 1st of March or any day in the year. In fact, I think because there is so much pressure to try and think of something that you want to change in terms of your behaviour, I think it can backfire. I think people can have a go at changing their behaviour and be unsuccessful because their New Year's resolutions often were unrealistic or they weren't properly thought through.
Okay, and how important is having a plan for all of this?
Well, it's very important to have a plan because it's well established within psychology that people often intend to make changes to their behaviour, but for whatever reason they don't get round to making those changes. And one of the best ways that we can put our intentions into action is by forming a concrete plan specifying exactly what we're going to do in exactly which situation we're going to do it. So, for example, if you want to lose weight, then you shouldn't just set yourself a goal of losing weight. You need to think about what specific behaviours are you going to try and change in order to lose weight. So it may be that you want to, for example, eat fruit snacks instead of eating unhealthy snacks while you're watching TV. But then you can specify further to say, well, what I'm going to do is I'm going to identify particular events where I snack, for example, when I'm watching TV, and that's where I'm going to substitute in the fruit for the unhealthy food that I eat at present. So having a plan is very useful because it helps to specify the details of exactly what we're going to do. Just having a goal of changing your behaviour or even just achieving some kind of health outcome is not going to be as useful as having a plan that tells you exactly what you're going to do and in exactly which situation you're going to go about doing it.
Oh, I see. Because my New Year's resolution was to get fitter. So you're saying that actually I can't just be as broad as that. I have to have a real plan of break it down into the different components.
Yes, I think if your plan is to get fitter, then you need to think about which physical activities in particular are you going to do? And then having decided on that, and I'd argue that you should think that through very carefully because you want to make sure that you try doing physical activities that are realistic for you. Then you move to the next stage of saying, okay, in which specific situations am I going to do those particular behaviours? So you might say to yourself, for example, I'm going to go to the gym more, and when I go to the gym, I'm going to use the running machine. In which case, the next step is to say, when exactly are you going to go to the gym? Are you going to go on your lunch break? Are you going to go after work? You need to think about exactly when you're going to put these things into action. And the more specific you can be in that respect, the better.
And I have to ask, do you have a New Year's resolution for 2018?
I'm afraid I don't. Perhaps I'm becoming more sceptical over time. I don't have any New Year's resolutions. I also have 2 young children, and I found that the best form plans can fall by the wayside when you have young children. So no, this year I am not resolving to change my behaviour in any way.
Benjamin Gardner there from King's College London. So, Georgia, how is Dry January going?
It's going really well, actually. I'm really enjoying sort of Sunday morning, getting up before midday. That's really enjoyable. But I am drinking heinous amounts of tomato juice instead. What about you, Izzy? How is your gym resolution going?
I've joined a gym, but I have actually yet to step foot in it. So I need to work on that plan, take Benjamin's advice and keep working on that.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
And for the next part of the programme, we're handing over to Katie Haler, who's been dipping into the criminal side of chemistry on the hunt for the perfect poison.
Shakespeare's suicidal lovers, Socrates' state execution, Litvinenko's political assassination. Poisons in their many forms have been killing people for thousands of years and continue to do so today. In 2016, there were 3,744 drug poisoning deaths in the UK, according to the Office for National Statistics. I'll be finding out the deadliest drinks, what's lurking in our houses, and how forensic specialists track down toxins. But first, what is a poison? Lorna Nisbet from Anglia Ruskin University.
Anything in the world can be a poison, okay? And we have known that since about the 16th century was the term when that kind of came around. There was a physician called Paracelsus, and he is known as the kind of godfather of toxicology, for instance, because it was him that said that it was literally just about the dose that made something a poison.
Everything is poison. There's poison in everything. Only the dose makes a thing not a poison.
So if something's a poison, it's going to have acute adverse effects on you and potentially kill you. And realistically, that could be anything. So it could be water, for instance. That could be a poison at some point in time.
Now, if we were on the hunt for the perfect poison, and if everything in the world could technically be one, where do we start?
So something like water is not going to be the best thing to use as a poison. And the reason for that is that you need litres of water before it's going to start having an adverse effect on the body.
So dose is important, but what other traits make a poison particularly promising?
So realistically, if you are going to be sinister and try and get a poison, you want it to be something that you're going to need a small amount of. You need to think about how you're going to administer that poison as well. So if you're going to put it in a drink, for instance, you need it to not taste of anything, and you need it to actually dissolve in that fluid if you're putting it in a fluid, and you need it to not smell either or change the colour of the drink. Not that I'm suggesting anybody poisons anybody.
Forensic scientist Lorna Nisbet there from Anglia Ruskin University. As the old saying goes, an apple a day keeps the doctor away. But eat enough apples in their entirety, and you could, in theory, risk cyanide poisoning from all those pips. But now we know the ingredients of a good poison, low fatal quantities, being hard to detect. Do we have any good, or should I say bad, candidates? The history books may be a good place to start looking. Chemist and author John Emsley knows his primitive poisons. He explained how the Victorians' poison of choice was one readily available in the pharmacy, which meant some rules had to be put in place.
To purchase poisons from a pharmacist, you had to sign the poisons register, and the pharmacist had to recognise who you were. You couldn't just walk into any shop and buy it. And so that was done because there were too many murders, mainly with something like arsenic, as its oxide was known as white arsenic, and this was widely used as a vermin poison and things like this. Colouring agents could be made from it. So it was available. Because it was available, it was being used to dispose of unwanted relatives and things like that.
OK, so are there any particularly famous cases of this?
Well, there's some very famous cases in history, but going back even earlier to the 17th century, the Marquise de Brinvilliers in France murdered her relatives to secure the family income. And she was only detected because the man who was supplying it, her lover, supplying the poison, suddenly died, and they discovered her letters. And the thing about that was, this is one of the first cases in which someone was asked to prove that the powder they detected was the deadly poison. And so that was in 1676. And a pharmacist in Paris devised a set of tests to prove that what they'd found was actually arsenic, and it worked, and she was found guilty and executed.
But what is it fundamentally about arsenic that makes it such an effective poison?
The thing is, it's in the same group of the periodic table as phosphorus. And phosphates, of course, are essential in lots of parts of the human body, from DNA upwards. And, of course, if you put arsenic there, the body can recognise arsenic and thinks it's getting phosphate. So it will introduce arsenic at all sorts of points. And then, of course, these things won't behave they should behave, and very quickly you're made very ill. And the body recognises arsenic as something it doesn't want very quickly, but not before it's absorbed quite a lot of it. And then, of course, it screws up various parts of your body, and you'll die. With a big enough dose, you'll die within a day or so. It will attach itself to something called ATP, adenosine triphosphate. And if it does that, then it really interferes because ATP is needed in every cell of the body. Then things begin to break down because you need ATP to generate energy. In your heart, for example, if you can't generate enough energy, then of course you're going to be in real trouble.
So the chemical element arsenic's availability and toxicity made it the perfect poison of the day. But it could be detected. So could a poisoner try to mask their ill intentions by using a substance that is already found naturally in the body?
Well, adrenaline is one that has been used in murders. The chemical name for it is epinephrine. And this, of course, the body produces, and it produces a lot of this if you're under sudden stress.
This is the fight and flight response, isn't it?
This is yes. If you're having a heart attack, they may give you this to stimulate the heart, keep it going. It's not something you would normally think of as being a poison, but it has been used by nurses. Nurses, of course, have access to it, and those are the ones who've generally murdered with adrenaline, because they know if you give too much adrenaline, it's going to overstimulate the heart, and the heart will pack up. The serial killer nurse called Kristen Gilbert actually probably killed about 50 of her patients with adrenaline. She worked at the Veterans Hospital in Northampton in Massachusetts, and she did it for a variety of reasons. If the persons began to annoy her, then she would give them an overdose. Often these people were very ill, and so it was just put down to the person had died of natural causes. But eventually she got rather careless in that if it was somebody in intensive care and she wanted to go out with her boyfriend and the person in intensive care couldn't be left, she would give them an overdose of adrenaline and pass them on to the next world. It's not known exactly how many people she dealt with, but it was probably around 50 before she was finally caught. And the thing about that was, it became so common, this occurrence of people she was supposed to be looking after suddenly dying, that they began to investigate. Other nurses said there's something odd about this. I think they called her the angel of death or something like that. They began then to analyse the body, and of course it was able to detect there was far more adrenaline in the body of the dead person than the body itself could have actually produced. And they were able to go back and analyse samples from bodies that had been dead 2 or 3 years, and there was still excess adrenaline.
So despite being a chemical that pre-exists in the body, even adrenaline can't stay hidden for long when given in lethal doses. So how about something so deadly, something which is needed in such a small quantity to cause harm, that it's virtually undetectable?
Well, the thing about polonium chloride is that it's radioactive, but it gives off only alpha particles. Now, alpha particles are relatively harmless. A sheet of paper will stop an alpha particle. It doesn't give off gamma rays. Now, gamma rays are the things that you can use a Geiger counter to detect. With polonium, it was possible, the Russian secret police found, to pass through the parts of airports where, you go through a thing and it's going to detect if there's anything radioactive on you. They could pass through that. So they were using this to dispose of people. Now, the amount of polonium you need to kill someone is so tiny, it's difficult to see. It's as small as a mote of dust. It is that deadly.
Polonium is radioactive. Once inside the body, the alpha particles emitted by polonium can make their way into cells, damage DNA, and cause cell death.
Now, we know our cells have got a wonderful repair mechanism that's being used all the time because, cells are needing repair. And of course, it can be repaired, but not when you're giving off something like 100 million of these particles a second. Then there's no way the body's going to be able to cope with that. Now, the most famous poisoning of this was someone called Alexander Litvinenko. And he came to Britain. He was a KGB agent, of course, and after the end of the Soviet Union, a lot of people from Russia could then come and live in Britain. He came to Britain and he was granted asylum because he said, I was ex-KGB, and he was able to tell the British secret people a lot about it. And so we took him in, and he was given another name. He was called Edwin Redwalt Carter, and he was given a house for him and his family in Muswell Hill in London, and he began to lead a quite anonymous life. The trouble was, when he was visited by his wife's mother, she went back to Russia, and the police there knew who she was. They searched her luggage, and they found out details of who he was and where he lived. And so they then sent another agent to London to dispose of him, and that agent came with polonium chloride. He was an old friend in inverted commas, of Litvinenko, and he invited Litvinenko to the Millennium Hotel where he was staying in London, and there he had green tea with polonium chloride in it. And of course, the following day began to feel ill. The doctor diagnosed gastroenteritis, the usual reaction to something you've eaten. put him into hospital. He got no better. Sent down to University College Hospital because he obviously was seriously ill. His hair began to fall out, which is sometimes a sign of thallium poisoning. Now, thallium's a deadly metal, but they tested for thallium. No, it wasn't thallium. And so they knew his hair was falling out because of radiation damage. The chemists, the scientists, detected polonium, and suddenly it was obvious what was killing Alexander Litvinenko, and he died after about 3 weeks in hospital.
Death by radiation. No taste, no smell, and given in minuscule quantities. It's polonium's volatility that led to its detection. Once identified, scientists were able to detect the traces it left behind on various surfaces, even including the seat in Arsenal Football Stadium where the killer had sat to watch a match.
We are only talking now of a few atoms, and yet there it is, and there it can be detected. Even that supposedly undetectable poison that the Russians were using is now no longer in that category of undetectable.
John Emsley there. Though unnervingly effective, once household products like arsenic, compounds already in the body like adrenaline, or even radioactive substances like polonium didn't escape detection. But how are poisons detected today? Back to Lorna, one of the many forensic scientists who identifies poisons, sometimes in deadly cases.
This machine here is a gas chromatography mass spectrometer, and it's actually two instruments that have been coupled together. So you have the gas chromatography side, and then you've got the mass spectrometer side. Your sample, your poison, will go into a vial, and the instrument will take it in a syringe, and it will inject it into the GC. At that point, it will become a gas, and that will separate out all the different components that would be in that sample. Because unfortunately, when people do pass away, or they have got an acute reaction to a drug or another poison, they might not have just taken one. So we need to separate out all those different components to see what is in that sample.
So are we putting blood or some sort of bodily fluid in here?
So you don't put the bodily fluid, you do some clean-up beforehand, but it would be like that. And then it will travel through the GC, and the GC is made up of a column that's 30 metres long. And it doesn't look like it's 30 metres long. And it is extremely thin and all coiled round and round and round, so it's quite compact. And then it will travel through to the mass spectrometer, and here it gets bombarded by electrons. So it goes past something that looks like a filament in a lamp, effectively. Okay. And it goes into what's called the mass spectrometry source. And from that point, because it's getting bombarded by these electrons, it causes your compound to fragment. And the idea is that every compound has a different fragmentation pattern. So it's like a fingerprint.
So if you know the fingerprint, you can tell what it is.
Yes, exactly. And if you have something, and once you've identified what it is, you can put down something that you think is the same. And if it's got the same effectively fingerprint, you can confirm that that's what it is.
Lorna Nisbet there. In the next part of the programme, we'll find out about one of the most toxic substances known and which cleaning products you definitely don't want to mix. From historical cases to the present day, so far we've only considered intentional poisonings. But what about accidental ones? According to the NHS website, most cases of poisoning occur in the home. So are there compounds lurking around the house that we should be aware of? I put this to toxicologist Robert Chilcott from the University of Hertfordshire.
Well, if we stick to the consumer products, one of the more interesting ones is botulinum toxin. Sometimes, if food has not been processed properly, things which are boiled and stored in jars or in tins can actually grow certain types of bacteria which produce botulinum toxin. Botox.
That's right, you heard correctly. Botox is the same stuff that some people have injected into their faces to relax facial muscles in order to reduce the appearance of lines and wrinkles. It's the same toxin.
It only accounts for a very small fraction of a percent of all reported food cases, but it's really the one you don't wish to have. It nearly always requires hospitalisation, and about 1 in 10 people who get botulinum toxin will actually die. The medical form, of course, is very pure, and it's a specific form of botulinum toxin. In the wild, there's about 7 types of botulinum toxin, but they all have the desired effect. They're incredibly toxic. And I think botulinum toxin is probably the most toxic substance that we're aware of.
So bacteria produce this toxin, and this bacteria could be around in the food that goes into the can. So what happens then? How, if you're unlucky enough to eat this food, what happens to your body?
Well, the bacteria that produce the toxin are pretty much ubiquitous. It grows nearly everywhere. So it almost certainly will be in the food that you try and preserve. The problem comes when you don't follow the right instructions. So, for example, if it's not boiled properly, or if you keep it in a solution which is not sufficiently acidic, then you run the risk of the bacteria starting to produce the toxin, which is primarily under what's called anaerobic conditions. So anything which doesn't have too much oxygen in will be a nice breeding ground for botulinum. As I said, it's an incredibly toxic material. The estimated lethal dose is about 70 nanograms. A nanogram is about 1,000 millionth of a gram. So it's very difficult to put that weight or lack of weight into perspective. But as a rough guide, if you think about a single human hair, that would be about 9,000 times heavier than a lethal dose of botulinum toxin.
Is this something that we should worry about as consumers of tin foods? Or does the problem come when you're making your own tin food?
I think the mass market, as the processing now is to a point where we don't need to worry about this at all. Of course, if we lived about 100 years ago when tin food was just coming into fashion, that was probably more a game of Russian roulette. So the most common forms of botulinum toxin these days is people who preserve the food at home, pickles and so forth, and things which goes into jars, fruit in particular, because sometimes it lacks the acidity that you need to prevent the botulinum from growing. But in general, it's actually, as I've said, a very rare form of food poisoning.
And why is it so poisonous? What does this toxin do when it gets into the body?
Put it simply, the botulinum toxin works by turning off our nerves. So, as you probably know, nerves normally activate muscles using substances called neurotransmitters. And these are chemicals that are released from the nerve endings and result in the coordinated movement of muscles. So, when we speak or walk or breathe, this is all down to the nervous control of our muscles. Basically, the toxin acts by cutting off the ability of the nerve endings to produce the neurotransmitter. So essentially that stops the muscle from being told to contract, and eventually it just causes paralysis. What's particularly nasty about botulinum toxin is that you get these paralysis effects and eventually you are unable to breathe, but the whole time you're actually conscious and aware of what's going on. There is an antidote. It's based on antibodies that actually bind to the different types of the toxins. There are actually 7 different toxins in botulinum toxin. So if you manage to get to a hospital and you get diagnosed, then that antidote may be available. Otherwise, the only treatment really is supportive. You may need to have mechanical ventilation. But botulinum poisoning can actually last quite a long time. So you may actually still suffer different degrees of paralysis for many months after you've initially been poisoned.
Wow, so if you're thinking about making your own tinned foods, you do need to be exceptionally careful. What about non-consumer products then? What about, for example, cleaning products? Can they be poisonous?
Oh, there's a whole wealth of poisons in cleaning products. The obvious example may be chlorine. Most people have heard of chlorine, but it's a bit of a two-edged sword when it comes to our society. On the one hand, you have your chlorine-containing consumer products that keep our world nice and clean and fresh and free from major diseases. But of course, if you mix the wrong types of cleaning products together, you can actually quickly produce lethal quantities of chlorine. It's not uncommon. I think in the UK each year, there's about half a dozen major incidents involving public exposure to chlorine. There are probably a small number of incidents involving single people that have mixed these chemicals in their toilet. But chlorine is actually quite toxic. It's a very highly reactive molecule, and it likes to seek out moist areas. So when you breathe it in, the nice wet lining of your lung tends to absorb the chlorine. There's no specific mechanism of action. It's just nasty corrosive stuff. So in a sufficient dose, you get the chlorine inside, and it'll basically just rot the lining of your lungs. That then causes a condition called pulmonary edema. So basically, all the fluid that's inside our body starts to leak into the lungs, and it stops us from breathing.
What kind of toxic combination are we talking about?
Well, The rough rule of thumb is don't mix cleaning products, but the particular cocktail which has the worst effect is mixing a bleach solution with anything which is acidic or contains ammonia.
Household bleach contains sodium hypochlorite, a chlorine compound. It's a common cleaning product, often used as a disinfectant to clean toilets, swimming pools, and even to treat public water supplies. But when mixed with other cleaning products, toxic gases can be released. For instance, chlorine gas in the case of mixing with acidic substances, or chloramine gas in the case of mixing with alkaline products like ammonia.
The initial signs of poisoning are at relatively low concentrations. It'll cause mild irritation of the eyes and the lungs. So basically, it'll be like going to a swimming pool for maybe an hour or so. You'll get a bit of red eye, maybe a little tickly cough. But when you actually start to get exposed to a higher concentration, it can actually get quite painful to breathe, and breathing just becomes much more difficult. And when you go to very high levels, so we're talking about 300 parts per million or so, you can actually die within 30 minutes of exposure. People often talk about antidotes to poisons, but I think there's only maybe about a dozen antidotes in the whole world for very specific chemicals. Unfortunately, chlorine is not one of them. So basically, if somebody gets exposed to chlorine and has these severe effects, the only way to treat them is supportive. So you give them some oxygen. You may want to give them some drugs to open up the airways, which are known as bronchodilators, possibly steroids to try and reduce the inflammation. And if they're lucky, it can take maybe 3, 4, 5 weeks to recover from a significant exposure to chlorine.
Scary stuff there potentially, but it's important to put this in context. Whilst Robert said that Botox may be the most toxic known substance, we are not all tinning our own food. Similarly, though bleach products are widely available and can be very poisonous, it's the chlorine or chloramine gas given off when cleaning products are mixed that's the problem. The poisons we've discussed so far are, thankfully, all detectable, and there are things we can do to reduce the risk of accidental poisoning. So where does this all leave our search for the perfect poison? John Emsley.
I don't think there is one now. Because of high-performance liquid chromatography, which can separate every component of a mixture, along with mass spectrometry, which can identify anything that's present, there's no way, once you suspect somebody has died of poison, even a tiny strand of their hair, analysed by this technique, will reveal what it is. If that's assuming that a little of the poison has got into the hair, which often it does. So there's no such thing anymore as a perfect poison. Even something, like adrenaline, which looked to be a perfect poison for this awful woman in America, she had to use so much of it. Of course, she needed to do that in order to wreck the heart, as it were. And of course, once that person's died, there's a residue of this at a higher level than nature can provide. So I just don't think there is such thing now as a perfect poison.
Good news. Reassuringly, John thinks there's very little chance of a poison being able to escape our modern detection methods once a poisoning case is suspected. But it's one thing to have the benefit of history and hindsight, looking at compounds we know and understand. What about new compounds? According to the Office for National Statistics, deaths from new psychoactive substances are on the rise. Here's Lorna again.
So if I'm going to stand up in court and say, or put to a pathologist, this is my toxicology report, this is what I have found, I have to be able to be confident that I have found what I'm saying that I found. And in order to do that, I have to have a reference standard, or I have to have a copy of what's called its mass spectra in a library. So you can't compare an unknown and magically know what it is. You're comparing your unknown with a known. Right? So if I do not have a reference standard or a spectra of some sort to compare, I cannot go into court and argue that that is definitely what it is.
Compound to compound, you cannot guarantee that is the same.
No, you would have to know you would have to be able to compare a known, and an unknown so that you can say that this is what this definitely is, and you have to be able to prove the evidence for that. Now, if these reference standards and if these spectra have not been done for that compound yet, so for instance some of the new psychoactive substances, we're struggling to keep up with them. About 2 a week come into Europe right now. So realistically, we have more now new psychoactive substances around than we do have of the classical drugs. So that can become a little bit needle in the haystack.
And in terms of poisons, I'm assuming people don't take psychoactive drugs because they want to poison themselves. They take them for their intended effect. Can a psychoactive substance be a poison?
Yes, it can, but it depends on the side effects of that psychoactive substance. So the toxicity is what you're looking for, and normally with like really, really classic drugs, they would do LD50. These are what it takes to kill 50% of a population. Some of these drugs have very high LD50s, or they're just unknown completely. So LSD, for instance, most of the deaths from LSD come because unfortunately somebody has fallen from a building, for instance. It's through a mechanical death rather than the actual drug. But the newer versions of them, which are called N-bombs, are much, much more potent, and you don't need the same amount that you need. The onset of them is slightly slower, so people tend to redose, and unfortunately that's how they die.
So maybe the ultimate killer compound is yet to be detected. From arsenic through to adrenaline, polonium, Botox and chlorine, we've only scratched the surface of the long list of substances that could do us harm. It's good to know that current detection methods make it difficult for malicious compounds to avoid being identified, and poison is hardly the weapon of choice for murderers these days. But the problem of accidental poisoning remains a significant one. 2016 figures from the Office for National Statistics show that over 7,000 people in the UK alone died from alcohol, a recreational drug. So whilst poisons perhaps shouldn't keep you up at night, knowing the chemistry of your compounds could help to keep you safe and well.
And that is all we have time for. Thanks to the guests there, that was John Emsley, Lorna Nisbet and Robert Chilcott. And thanks to Katie Haler for putting the programme together. Do join us next week for one of our Q&A shows. In the spirit of our own doomed New Year's resolutions, we'll be answering questions about diet, exercise and sleep to start 2018 in the best of health. Do join us then. The Naked Scientist comes to you from Cambridge University and it's supported by the STFC, the EPSRC and Rolls-Royce. I'm Georgia Mills and thank you very much for listening.